In this video, I'm going to look at absolute and conditional convergence. So I'll start with absolute convergence. Now, suppose the sum of S sub n is a series that is convergent, then if the sum of absolute value of S sub n converges, then that series is said to be absolutely convergent. All right. For example, here we have an alternating series, and just by inspection, this series converges by alternating series test. So this converges by alternating series test, and if you take the summation of absolute value of S sub n, like what we can see here, this series also converges by p-series test. Therefore, we say this series is absolutely convergent. Okay. However, if the sum of S sub n diverges, then the series is said to be conditionally convergent. So, for example, here we have a series, alternating series, that converges by alternating series test. Okay. But if you take the summation of absolute absolute value of S sub n, then we end up with a harmonic series, and this series diverges by a p-series test. All right. So this series is conditionally convergent on condition that we do not take the absolute value of its terms. So this brings us to the absolute convergence theorem. Now, the absolute convergence theorem states that series that are absolutely convergent are guaranteed to be convergent. So basically, if the series converges, so suppose you have this series which converges, right? If you have this series that converges, then this series also converges, right? So you just have to show that the sum of absolute value of S sub n converges, then you can say that by absolute convergence theorem, the series converges. All right. However, you have to remember that the converse of that statement is not true. Right. What I mean here is series that are convergent may or may not be absolutely convergent. For example, this alternating series here is convergent by alternating series test, but if you take the summation of S sub n, then you end up with a harmonic series which is divergent. So you have to be careful with that. All right, let's look at an example. So show that the sum from n is equals to 1 to infinity of cos n over n squared is convergent. So what's the plan in this question? The plan is we can use actually what we've just discussed. We can show that yes, we can show that the sum of S sub n converges. Then you can conclude that the sum of the series converges by the absolute convergence theorem that we just discussed here. So what I'm saying here is we can use this theorem here, right? Absolute convergence theorem to show that this series is convergent. So this is the plan. We can show that we can start by showing that the sum of S sub n, by the way, S sub n here is cos n over n squared. So we can start by showing that the sum of S sub n converges. Then we can conclude that the sum of the series converges by um, absolute convergence theorem, or theorem of absolute convergence, so theorem of absolute convergence. Okay, so this is the plan. This is what you're going to do. We're going to show that the sum of S sub absolute value of S sub n converges. Then we can conclude that the series converges by theorem of absolute convergence. All right. So I'll start first of all by showing that this series, the series, the sum of S sub n, absolute value of S sub n converges, and we can use the comparison test. So we can go ahead and form an inequality and use comparison test to show that the sum of absolute value of S sub n converges. Okay? So this is what I mean. Let me just highlight. We want to show that this converges. And what I'm trying to say is to show that you can use comparison test. Okay, that's a plan. Anyway, so we have to work this out. So we can form an inequality. We know that the absolute value of cos n is between 0 and 1. So absolute value of cos n is between 0 and 1. And then what I'm going to do is to divide both sides by n squared. So by n squared, by n squared, by n squared. So we'll have this inequality. We'll end up with this inequality. Actually, I can just write it as over n squared, 1 over n squared. All right. Now, we know that the sum of 1 over n squared converges by p-series test, which means the sum of the absolute value of cos n over n squared will also converge by comparison test. So what I mean here is since the sum from n is equals to 1 to infinity of 1 over n squared converges by p-series test, then the sum from n is equals to 1 to infinity of absolute value of cos n over n squared converges by comparison test. Okay? So we can say that by the theorem of absolute convergence, the sum of A sub n is also convergent. So by the theorem of absolute convergence, the sum from n is equals to 1 to infinity of cos n over n squared is also convergent. Okay, now to example 2. Show that the sum of this series is convergent. So what's the plan? The plan is we can start by showing that the sum of the absolute value of S sub k converges. Then we can conclude that the sum of S sub k converges by the theorem of absolute convergence. Now, what I'm saying here is S sub k is sine k over k squared. So we can show that the sum k is equals to 1 to infinity of absolute value of S sub k converges. Then we can conclude that the sum from k is equals to 1 to infinity of S sub k converges by theorem of absolute convergence. Okay, so that's our plan, and now we have to start working this out. So we have to show that this bit here converges, right? We have to show that that bit there converges. And what that means is we have to show that the sum of absolute value of sine k over k square converges. Now, what we can do is we can use comparison test again. So, just here, we can say use comparison test. So, using the comparison test, I know that, or we know that, sine k is actually between the value of absolute value of sine k is between 0 and 1. So what we can do is we can divide each of this side by k squared just to get what you want. So we can say that you know sine absolute value of sine k over k squared, you can write it like that, is between 0 and 1 over k squared. All right. So what we can do here is, the most important thing is the inequalities. Why? Because what I want to do is I want to use the comparison test. Okay. Now, since now we know that this bit here, converges by P series test. So this converges by P series test. So the fact that it converges by P series test, it means that the absolute value of sine k over k squared, remember k is greater than or equal to 1, so that's why it had the absolute value sign going all the way to the denominator. But anyway, if the sum of 1 over k squared converges by P series test, then because the absolute value of sine k over k squared is between 0 and that, it means that it also has to converge by comparison test. So what I mean is this, just write it as a statement to avoid the confusion. So since the sum k is equals to 1 to infinity 1 over k squared, Okay, now that we know that the absolute value, the sum of the absolute value of S sub k converges by comparison test from what we discussed above, we can now say that we can now apply the absolute convergence theorem and say that hence the sum of S sub n converges by absolute convergence theorem, or by the theorem of absolute convergence. All right. So that's how you approach a question like this one. Start with the plan, and then once you understand what you're doing, you should be able to carry through to your final solution.